So welcome to module 12. This module is about transformation of discrete random variables. So suppose x is a discrete random variable which is defined on some probability space omega p, and suppose fx is a distribution function of x. Fx is the probability mass function because we are talking about a discrete random variable, so that is why we are talking about probability mass function. Now this x suppose has support Sx. Now we know that for the discrete random variable, support is same as the set of discontinuity points of fx, so this is same as dx. And suppose h is a real valued function defined on real line. Now in many situations, we may be interested in knowing the distribution of a random variable y, which is same as hx. Note that hx is a random variable because x is a random variable. So the values of hx are also random. When I say probability distribution, it means distribution function or the probability mass function or the PDF of hx when we know what is the distribution function or probability mass function of x. Note that x has support Sx. So that means x takes only values in Sx with positive probability. So that way, if I define h of Sx as the possible values of h which will be taken with positive probability, that would be collection of all those hx such that x in Sx. So in a sense, this is a image of Sx under h. So let us look at an example. So for example, if my Sx is this, then h of Sx would be this, provided h is like this. So this h of Sx is image of h under Sx. Now for a given y belonging to h of Sx, I define h inverse y as collection of all those x's which are mapped to y. So for example, if my sy is over here, and let us look at, I am looking at this point y. So this is basically would be a set h inverse y. So if this is y, this would be h inverse y. So these are collection of all those x's such that image of them is same as y. Now note that Sx is a countable set. So h of Sx would also be a countable set because h of Sx in fact would have a smaller number of elements than Sx, because what would happen is because h is function, so there is a possibility that here more than one point from x are going to the same point in h of Sx. So it looks like h of Sx is going to be a support of the random variable y, which is h of Sx. So to that, let us look at any point y in HSX. If y is in HSX, that means h of x0 is same as y for some x0 belonging to Sx. Then probability y is equal to y is same as probability hx equal to y. But y is same as h of x0 for a given x0. So this is same as probability hx equal to hx0. But this probability would always be greater than or equal to x equal to x0 because x equal to x0 implies that h of x is same as h of x0. So this event implies this. So probability of this event would be less than or equal to probability of this event. So or in other words, probability of this event would be greater than or equal to probability of this event. So that is what is happening over here. Probability of this event is greater than or equal to probability x equal to x0. But x0 was in Sx, so probability x equal to x0 is positive. So what we have proved is for any y in HSX, probability y is equal to y is positive. Now we'll also prove, if I can prove that summation over y belonging to HSX, probability that y is equal to y is 1, then it will turn out that y is a discrete random variable with support as h of Sx. So that is what we'll do next. So let us look at what is the probability that y belongs to HSX. But y is same as hx, so this is same as hx belongs to h of Sx. But hx belongs to h of Sx if and only if x belongs to Sx. That is very obvious because if x belongs to Sx implies h of x belongs to h of Sx. Now if h of x belongs to h of Sx, by definition of h of Sx, this is same as collection of all those hx such that x belongs to Sx. So if h of x is belonging to this, that means h of x has to be in, that means this x has to be in Sx. And probability x belonging to Sx is 1. So thus, there exists a countable set HSX such that probability y is equal to y is positive for every y belonging to HSX. And probability that y belonging to HSX is 1. So this proves that y is a discrete random variable with support as Sy, which is same as h of Sx. Let us try to see what would be a probability mass function of y. So support is Sy, so I look at for y belonging to S of y, which is same as h of Sx. Probability y is equal to y. Probability y is equal to y is same as probability hx equal to y. Hx equal to y happens if and only if x is in h inverse y. Now x is only taking discrete values, so this would be collection of all those x belonging to h inverse y, fx x. So I can get the probability mass function like this. So this is what the result says. The random variable y is equal to hx is a discrete random variable with support Sy, which is same as h of Sx. And probability mass function is obtained by summing the probability mass function of x over all x such that x belongs to h inverse y. And this would be 0 otherwise, because Sy is the support of y, so outside Sy, Fyy would be 0. Now let's take this example. Suppose your fx is this. So this is a distribution function of a random variable x. It is easy to see that this is a proper distribution function. And suppose I am interested in probability mass function of y is equal to 2x squared plus 1. I can do it in two ways. The first part says find the distribution function of y first, and hence find the PMF of y. In the second part, I say first find the PMF, and from the PMF, you find the distribution function of phi. So first, I'll try to find out what is the distribution function of phi. Note that I already know that y is a discrete random variable. So I need to look at what is my Sy, that is the support of y. Note that if I look at this distribution function clearly has set of discontinuities as -1, 0, and 1. And probability that x belongs to dx would be same as probability x equal to -1 plus probability x equal to 0 plus probability x equal to 1. And you can easily check that this turns out to be 1. So x is a discrete random variable with support as -1, 0, 1. Now if x has support -1, 0, 1, finding the support of y is not difficult. So I look at y is equal to h of Sx. My hx is 2x squared plus 1. So when x is -1, y takes value 3. So 3 is there in the support. When it is 0, it takes value 1. So 1 is in the support. When x takes value 1, y takes value 3. So 3 is also there. So that means my support of y is just 1 and 3. So by last result, y is a discrete random variable with support Sy as 1 by 3. Now note that y takes only value 1 and 3. So when I am talking about Fyy, which is same as probability that y less than or equal to y. Now this capital Y cannot take value less than 1. So if y is less than 1, my Fyy would be 0. Similarly, if this small y was greater than or equal to 3, then I know that capital Y is always takes value less than or equal to 3. So for y greater than or equal to 3, Fyy would be 1. Now I try to find out what is the distribution function in the range y between 1 to 3. So Fyy is same as probability y less than or equal to y, which is same as 2x squared plus 1 is less than or equal to y, which is same as x squared is less than or equal to y minus 1 by 2, which is same as x lies between minus square root y minus 1 by 2 to square root 1 y minus 1 by 2, which is same as fx of square root y minus 1 by 2 minus left hand limit, because equal to is included here. So it will be distribution function of x at the point minus square root y minus 1 by 2, and I have to consider a left hand limit over here. So fx minus square root y minus 1 by 2 minus. Now note that y is between 1 and 3, so y minus 1 by 2 is between 0 and less than 1. So and minus y minus, so its square root is also between 0 and 1. So minus square root y minus 1 by 2 is between minus 1 to 0. So I look at distribution function of this quantity when the argument is between 0 and 1. Argument between 0 and 1, this is half. When argument is between minus 1 to 0, the value is 1 by 4. So this is argument between 0 and 1, half. This is argument between minus 1 to 0, value is 1 by 4. So 1 by 2 minus 1 by 4 is 1 by 4. So I have found out the distribution function at all possible ranges. And my distribution function that way becomes this. Once I know the distribution function, I can find out what is probability mass function. I know the support of y is 1 and 3. So that means y will take only value 1 and 3 with positive probability. So I find out fyy, which is probability y is equal to y, which is same as fyy minus fyy minus. First I find at y is equal to 1. So fy1 minus fy1 minus. So this is fy1 is 1 by 4 minus fy1 minus is 0. So 1 by 4 minus 0, it becomes 1 by 4. At y is equal to 3, fy of 3, which is 1, minus fy of 3 minus is 1 by 4. So 1 minus 1 by 4, which is 3 by 4. And this will be 0 otherwise, because 1 and 3 is only the support of y. You can easily check the total sum has to be 1. 1 by 4 plus 3 by 4 is 1, because it is a discrete random variable. So it is a probability mass function. The other way is I can find out the probability mass function directly and then can find out the distribution function. So PMF of x we have already found, because dx is minus 1, 0, 1. Probability x equal to x is same as fx x minus fx x minus. For example, when I look at x equal to minus 1, so this would be same as fx minus 1 minus fx minus 1 minus. If I go back, I look at fx1 is 1, fx1 minus 1 is, fx minus 1 is 0, fx minus 1 is 1 by 4, fx minus 1 minus is 0. So this turns out to be 1 by 4 minus 0, which is 1 by 4. Similarly, x equal to 0, fx0 minus fx0 minus. I go back, I look at fx0 is half, fx0 minus is 1 by 4, so it becomes half minus 1 by 4, which is 1 by 4. Now similarly, you can find x equal to 1, which is fx1 minus fx1 minus, and this will turn out to be half. And this will be 0 otherwise. So I have the probability mass function of x. Now using this probability mass function of x, I'll try to find out the probability mass function of y. So fyy is probability y is equal to y, which is same as probability 2x square plus 1 is equal to y, which is same as x square is equal to y minus 1 by 2, which is same as x belong to minus square root y minus 1 by 2, or x is square root of y minus 1 by 2. Now my sy is 1 and 3. So I try to find out my probability mass function at only these 2 points, because at rest of the point I know that probability mass function is 0, because sy is the support of y. So at y is equal to 1, these two quantities are same, so this is same as probability that x belongs to the singleton 0, which is same as probability x equal to 0. And probability x equal to 0, we can get it from the last table as 1 by 4. If y is 3, this is same as probability that 3 is 3 minus 1 by 2, which is square root of 1, so minus 1, 1. So probability that x belongs to minus 1 and 1. Now this is same as probability x equal to minus 1 plus probability x equal to 1. I've already found out the probability mass function of x. So these values I can get from probability mass function of x. So let us look back. X equal to minus 1 is 1 by 4. X equal to 1 is 1 by 2. So this probability becomes 1 by 4 plus 1 by 2, which is 3 by 4. So you get the probability mass function. Now I have a probability mass function, so I can get the distribution function. Note that my Sy is 1 and 3. So Fy, which is same as probability y less than or equal to y. Now if my small y was less than 1, then I am saying that capital Y takes value less than 1. But capital Y cannot take value less than 1 with positive probability. So this probability is 0. Now, if y is between 1 and 3, I am saying my capital Y takes value less than or equal to this small y. Then the only possible value in Sy is y is equal to 1. So which is same as probability y is equal to 1, which is same as 1 by 4. Then suddenly, if y is greater than or equal to 3, then what is the probability that capital Y takes value less than or equal to this? But capital Y takes only value 1 and 3, so probability y less than or equal to y happens with certainty, and that is why this probability is 1. So I found out the distribution function. Now let's consider the following example. Suppose x is a random variable with probability mass function as this, 1 by 2 to power x, if x is 1, 2, 3, so on, and 0 otherwise. This is clearly a proper probability mass function. You can sum it over Sx, fxx. This is 1, where my Sx is the point where it takes the values with positive probability, which is 1, 2, 3, and so on. So clearly, Sy will take value x minus 1, so 0, 2 minus 1, 1, 3 minus 1, 2, and so. So my Sy becomes this. And I know that y is a discrete random variable by the result which we did. So Sx is this, y is hx equal to x minus 1. So S5, which is h of Sx, which is 0, 1, 2, and so on, as I showed. So probability mass function at point y would be probability y is equal to y, which is same as probability x minus 1 is equal to y, which is same as probability x equal to y plus 1, which is same as fxy plus 1. I have to find out this probability only when y is in the support. That means y is 0, 1, 2, so on. So for y is equal to 0, 1, 2, 3, so on. If y is between 0, 1, 2, 3, so on, y plus 1 belongs to 1, 2, 3, and so on. So it is fx when the argument is 1, 2, 3, so on. And I know that when argument is 1, 2, 3, so on, fxx is same as 1 by 2 to power the argument. Now in this case, since argument is 1, 2, 3, so on, fx of y plus 1 would be same as half to power argument, which is y plus 1. Y is equal to 0, 1, 2, 3, so on, and 0 otherwise. So this is another example. Now let me give the following take-home problem. So suppose x is a random variable with this distribution function as follows. Now determine whether or not x is discrete. It's very easy to check. Find out the set of discontinuity points of fx. Call that set as dx. If probability x belonging to dx turns out to be 1, it would be a discrete. Otherwise, it will not be discrete. So you can see, just by observation here, fx is a step function. For x less than minus 2, it is 0. So it is minus 2. Minus 2 to 0, it is 1 by 4. Then half, then it is 1. So it is a step function. So it looks like it would be a discrete random variable. Now I define another random variable, which is y is equal to x squared plus mod of x. Find the distribution function of y and hence the PMF of y. In the next part, first you find the PMF of y and hence find the distribution function of y. Now similar example we did earlier. So doing this should not be a difficult exercise. Now before I conclude, let me give a summary of the next module. So in this module, we saw how to derive the distribution of a function of a discrete random variable. In the next module, we'll see how to derive the distribution of a function of an absolutely continuous random variable. So the model will be as follows. So suppose x is an absolutely continuous random variable with distribution function fx and PDF fx. And suppose y is equal to hx is some real valued function defined on real line. We'll see under what conditions y is absolutely continuous. And if y is absolutely continuous, what is the PDF of phi? Note that in the discrete case, we saw that if x is discrete, this would clearly imply that hx is discrete. And we know how to find the distribution of phi. So similar thing we'll see in the absolutely continuous case, whether when x is absolutely continuous, can I say that h of x is also absolutely continuous? So that is something we'll address in the next module. This was all for this module. Thank you for your patience and have a great day.